When our prehistoric ancestors studied the sky after sunset, they observed that some of the stars were not fixed with respect to the constant pattern of the constellations. Instead, 5 of them moved, slowly forward across the sky, then backward for a few months, then forward again, as if they couldn't quite make up their minds. We call them planets, the Greek word for wanderers. These planets presented a profound mystery. The earliest explanation was that they were living beings. How else explain their strange, looping behavior? Later, they were thought to be gods, and then disembodied astrological influences. But the real solution to this particular mystery is that the planets are worlds, that the Earth is one of them, and that they all go around the sun according to precise mathematical laws. This discovery has led directly to our modern global civilization. The merging of imagination with observation produced an exact description of the solar system. Only then could you answer the fundamental question, the one at the root of modern science: what makes it all go? 2,000 years ago, no such question would even have been asked. The prevailing view had then been formulated by Claudius Ptolemy, an Alexandrian astronomer and also the preeminent astrologer of his time. Ptolemy believed that the Earth was at the center of the universe, that the sun and the moon and the planets like Mars went around the Earth. It's the most natural idea in the world. The Earth seems steady, solid, immobile, while we can see the heavenly bodies rising and setting every day. But then, how explain the loop-the-loop motion of the planets in the sky, Mars, for example? This little machine shows Ptolemy's model. The planets were imagined to go around the Earth, attached to perfect crystal spheres, but not attached directly to the spheres, but indirectly through a kind of off-center wheel. The sphere turns, the little wheel rotates, and as seen from the Earth, Mars does its loop-the-loop. This model permitted reasonably accurate predictions of planetary motion, where a planet would be on a given day. Certainly good enough predictions for the precision of measurement in Ptolemy's time and much later. Supported by the Church through the Dark Ages, Ptolemy's model effectively prevented the advance of astronomy for 1,500 years. Finally, in 1543, a quite different explanation of the apparent motion of the planets was published by a Polish cleric named Nicholas Copernicus. Its most daring feature was the proposition that the sun, not the Earth, was at the center of the universe. The Earth was demoted to just one of the planets. The retrograde or loop-the-loop motion happens as the Earth overtakes Mars in its orbit. You can see that from the standpoint of the Earth, Mars is now going slightly backwards, and now it is going in its original direction. This Copernican model worked at least as well as Ptolemy's crystal spheres. But it annoyed an awful lot of people. The Catholic Church later put Copernicus's work on its list of forbidden books. And Martin Luther described Copernicus in these words. He said, "People give ear to an upstart astrologer. This fool wishes to reverse the entire science of astronomy." Close quote. The confrontation between the two views of the cosmos, Earth-centered and sun-centered, reached its climax with a man who, like Ptolemy, was both an astronomer and an astrologer. Kepler worked with a kind of passionate intensity to understand Tycho's observations. What real motions of the Earth and Mars about the sun could explain to the precision of measurement the apparent motion, as seen from the Earth, of Mars in the sky. And why Mars? Because Tycho had told Kepler that the apparent motion of Mars was the most difficult to reconcile with a circular orbit. After years of calculation, he believed that he had found the correct values for a Martian circular orbit which matched 10 of Tycho Brahe's observations within 2 minutes of arc. Now, there are 60 minutes of arc in an angular degree, and of course 90 degrees from horizon to zenith. So a few minutes of arc is a very small quantity to measure, especially without a telescope. But Kepler's ecstasy of discovery soon crumbled into gloom because 2 further observations by Tycho were inconsistent with his orbit by as much as 8 minutes of arc. Kepler wrote, "If I had believed that we could ignore these 8 minutes, I would have patched up my hypothesis accordingly. But since it was not permissible to ignore them, those 8 minutes pointed the road to a complete reformation of astronomy." The difference between a circular orbit and the true orbit of Mars could be distinguished only by precise measurement and by a courageous acceptance of the facts. Kepler was profoundly annoyed at having to abandon a circular orbit. It shook his faith in God as the maker of a perfect celestial geometry. Having cleaned the stable of astronomy of circles and spirals, he said, he was left with only a single cartful of dung. He tried various oval-like curves, calculated away, made some arithmetical mistakes, which caused him, in fact, to reject the correct answer, and months later, in some desperation, tried the formula for the first time for an ellipse. The ellipse matched the observations of Tycho beautifully. In such an orbit, the sun is not at the center, but is offset. It's at one focus of the ellipse. When a given planet is at the far point in its orbit from the sun, it goes more slowly. As it approaches the near point, it speeds up. Such motion is why we describe the planets as forever falling towards the sun, but never reaching it. Kepler's first law of planetary motion is simply this: a planet moves in an ellipse with the sun at one focus. As the planet moves along its orbit, it sweeps out, in a given period of time, an imaginary wedge-shaped area. When the planet is far from the sun, the area is long and thin. When the planet is close to the sun, the area is short and squat. Although the shapes of these wedges are different, Kepler found that their areas are exactly the same. This provided a precise mathematical description of how a planet changes its speed in relation to its distance from the sun. Now, for the first time, astronomers could predict exactly where a planet would be, in accordance with a simple and invariable law. Kepler's second law is this: a planet sweeps out equal areas in equal times. Many years later, Kepler came upon his third and last law of planetary motion, a law which relates the motion of the various planets to each other, which lays out correctly the clockwork of the solar system. He discovered a simple mathematical relationship between the size of a planet's orbit and the average speed at which it travels around the sun. This confirmed his long-held belief that there must be a force in the sun that drives the planets, a force stronger for the inner fast-moving planets and weaker for the outer slow-moving planets. Isaac Newton later identified that force as gravity, answering at last the fundamental question: what makes the planets go? Kepler's third, or harmonic law, states that the squares of the periods of the planets, the time for them to make one orbit, are proportional to the cubes, the third power, of their average distances from the sun. So the further away a planet is from the sun, the slower it moves, but according to a precise mathematical law.